I guess we'd like to solve some nice problems. Some good old problems. And in order to do that, we will look into our favorite contestable Knuth. Let's go. There are several problems. I hope they are nice. I hope they're not hard. Oh, 8 problems. And sorry, but it seems like most of them are in Russian only. So little Petya loves rectangles. He gave his mom a list of rectangles. Each of them is of width W and of height H. Mom wants to buy all these rectangles, and the cost of the rectangle is equal to its area. And there is also a sale in this shop. So you can buy not one rectangle, but several rectangles. And if you buy several rectangles, then the cost of it is the product of the width of the most wide rectangle times the height of the most tall rectangle. You cannot swap width and height, and we need to buy to group these rectangles in such a way that we get the minimum possible cost. Okay, this is a standard problem on dynamic programming optimization. Okay, let's start with reading the input and then we will do the rest. So we need to read n. Then we need to read all the rectangles. rectangles V Okay. How to solve this problem? First of all, notice that if we have some rectangle and some smaller rectangle, then this rectangle does not interest us, because we can put anywhere where we can put this rectangle, we can also put this rectangle. So let's remove all small rectangles. How can we remove all small rectangles? Actually, really easy. Let's sort all rectangles. So sort V begin, V end, and let's make the new array, which consists only of such rectangles which are not contained in anything bigger. VPIW, and let's go through all vector P, vector V. So while something, we will pop back from W, and then we will push back there P. While what? We can pop back if V is not empty. And also what? And also, since we have this array sorted, we already know that P.x is at least V.x. Yeah, so we know P.x is at least V.x. So the only thing which is enough to remove it is if even y is also bigger or equal in rectangle P. V dot back. Okay, we have done it, and now we have all these rectangles in our array W sorted. So they are sorted by x. Let's say that this is x. The first coordinate is x, and the second coordinate is y. Then all these rectangles are sorted by x. So first of all, we have small x but big y. Then we have smaller y but bigger x. Again, smaller y, bigger x, etc. Okay. What now? Now we need to group them into several blocks, and in each block we put them all into one rectangle. Like this, for example. So how do we decide? Well, it's kind of straightforward. Let's write the problem, the dynamic programming problem. So we want to assume that we have n rectangles. Yeah, so n is w dot size. Let's say that Pi is the cost of taking first I rectangles. Okay? Then what can we do? Pi. We need to take some ji in a group, so cost of this half semi-interval. J runs from 0 to I excluding, and then plus Pj. Okay, what is this cost? It can be rewritten as what? So notice that inside this semi-interval we need to take the maximum x and maximum y. So x is sorted, so we need to take maximum x, which is xi minus 1, and maximum y is yj. So this is our thing. Notice that actually, if we denote fj a linear function which is equal to x times yj plus pj, then this is simply fj of xi minus 1. Oh, sorry, my camera is not working. So we have I functions of this form. We need to take the minimum value. And this is pi. Okay? Okay, can we actually take j equals 0? Yes, we can. Okay, so let's go through all numbers. So we have LLP, which is some answer. In the end, we will return if I equals n, we will return p. What is p? P is minimum value of all such functions in point xi minus 1. Yeah, so if I equals 0, then p is also 0, else p is some structure, find min of in point xi minus 1, which is simply w I minus 1 dot x. After that, we need to add a new function, exactly this function, which is fi of x equals xyi plus pi. So we need to add this function. Right? Yeah, right. So if I is less than n, we add it. So we add a new function. Let's store a linear function in a structure which consists like of int and long. Structure linear function which consists of int k and long b. So this is a linear function. And we add a linear function yi pi. So yi and pi, which is p. Great. So we need a structure convex Hull Trick, which stores a set of linear functions and which is able to find minimum among them. Well, actually, one more thing is for Convex Hull Trick, it is important that the lines are added in the decreasing order of their coefficient. But we will have that. Our coefficients are yi, and yi are actually decreasing. Yeah, you see? Each new yi is decreasing compared to the previous one. So that's why it will work. So how do we write these two functions? Okay. Convex Hull Trick. Convex Hull Trick will consist of two functions. So we will have to find mean in a point, and we will have to add some new function. So void add a linear R, linear L. Okay, how will we do it? So for each function, we will store starting from which point it is optimal. And we will remember that the first function is optimal. It is always optimal. Yes, so how can we write that? We will have a vector of pairs. So in each pair, first of all, we have a long starting from which this function is optimal, and a linear function which is optimal on this segment. Okay, this is functions. How do we add a new linear function? Well, first of all, we need to check, so while not f.empty and something. So first of all, we will need to remove some functions. And then if it's still not empty, okay, so we will have to write a, so if f is empty, then starting point is actually doesn't matter. For example, let's put 0. If it's not empty, then let's take what? Let's take the intersection of f and L. Actually, it should be an intersection which is rounded up. We will remember that. Intersect and rounded up. And we will push it. So we'll say that f dot push back. Okay, let it be in place back. Start and the linear function L. So what do we do here? Actually, let's check. So let's take f.back.x. This is the point. Let's put this point into f. F.back and in L. Okay, let's assume that in our stack, the last function in its breaking point is greater or equal than L. If it's true, then we really don't need this function. There is also one case. If f.back.y.k is equal to l.k. In this case, we simply don't need this function l. Else, break. Now we want to substitute a point into a linear function, and it's easier. That's it. Now we need to intersect two functions. So ll intersect linear A, linear B. It should be easier, so we have k1x plus b1 and k2x plus b2. And this is less than this. Let's assume that k1 is less than k2. Then where do they intersect? Actually, I want k1 to be greater than k2. So if a.k is less than b.k, then swap a and b. Actually, if a.k is equal to b.k, let's throw 0, for example, or anything else. Otherwise, k1 minus k2 x equals b2 minus b1, and x equals b2 minus b1 over k1 minus k2. But since we are interested in points starting from which it is optimal, we need to round it up. And to round it up, how do we round something up? How do we round a fraction up? So we need to take the numerator, which is b2 minus b1. b2 minus b1, so b dot b minus a dot b. And denominator equals a dot k minus b dot k. So we want to divide numerator by denominator and round it up. First of all, we know that the denominator is positive. So how do we round it up? We want to find the residue of minus numerator and add it. So we want to take minus numerator percent denominator. And if add is less than 0, add plus equals denominator. After that, we can return numerator plus add divided by denominator. After this manipulation, we have rounded it up. And this is the function intersect up. Okay, now we need the function find mean. To do that, we will have to find what do we have to find? We have to find the last moment, the last point, which is still at most x. Instead of that, let's find the first point, which is already greater than x. So how do we do it? We need an upper bound of f.begin, f.end, and we also need x, and we need a function which compares this pair and a point x. So how do we compare a pair and an x? We will need to check, is it true that g is less than x? We just need to check that g dot x is less than x. Is it what you need? Yeah, I think so. So we have found the upper bound. We need to subtract 1 from it. And after that, we're happy because we return it second of x. But did it work? It did not work. The problem is here. So we need to call this Convex Hull Trick. And here we need to declare it. What's wrong with you? It's not a part of linear. Okay, let's put it into linear. F f dot back dot y. I even don't know. I don't like this thing. Actually, it's not that bad, maybe. We need to swap them. Okay, I'm not too proud. Let's put it other way. So firstly we have const x, then we have this, and we check that x is less than g of x. Okay. Now it succeeded. I don't want to look at the problem details. Instead, let's look at the sample. Extraordinary. Let's take a look at 2 other samples. Okay, so assume that we have 99, 100, and 199. Or assume that we have 100, and 101. These are 2 different samples. In the first of them, we want take this, and the second, we want this. What about... and here is the combination, yeah? So we have 200 and plus 300, so 500. I think we can try to submit it. It's compilation error because I used C++ 20, didn't I? Okay, it was smooth. Bus stations. We have n houses along a road. Ith house has a coordinate xi. We want to put several bus stations, and inconvenience of a house is the square of the distance between this house and the nearest bus station. We want to put k bus stations to minimize the sum of inconveniences of all houses. So we need to minimize this function. Okay, let's solve this problem. So again, as it was said earlier, we have several points. X, let's start with 0. Actually, we want to sort them in the beginning. So they are not sorted, but indeed we will want to sort them. And kx. For now, let's remove Convex Hull Trick. Maybe we will return it later. So we have VIXN and K vector int read VI and find dance of X, and it will be a float, so we will need these primitives which are included in IO manip. So here we will return float given VIX. So first step is to sort X. Okay, after it's sorted, notice that each byte station, it serves to a segment of houses. So it's there's no, it doesn't make sense for some person to go here, but for some person here to go here. If these segments overlap, then it's not optimal. Well, after that, we can, instead of taking bus stations and choosing people for whom this is the nearest one, instead we can firstly divide all houses into segments, and then in each segment we can choose the point in which it is optimal. So assume that we have a point. Yes, so we have x1, etc., xn. Xi, etc., xj minus 1. So where do we need to put this point? So we pay x, assume that we put it in point B. Then we have some xi minus b squared, which is sum of b squared minus 2bxi plus xi squared. And we want to minimize it. So for minimization, this doesn't change anything because it is a constant. So sum of b squared is just j minus I b squared minus 2 times b times sum from I to j minus 1 xk. Not k, for example, L. L is fine. L is not used. Okay. And now let's take a first derivative. So we want to minimize it. So we want the first derivative of this thing to be 0. The first derivative becomes 2j minus I b minus 2 times this sum equals 0. And this means that b is sum of xl's over j minus I. Okay, we know this optimal point, but we also need to find the cost of this segment. What is the cost of the segment? The cost of the segment is now... So we know that it's just an arithmetic mean. Yeah? So the cost of the segment is sum of bi minus arithmetic mean squared, where this is mean. xi minus b, sorry. x L minus b, L from I to j minus 1, and this thing squared. Again, as I said, this is sum from from I to j minus 1, xl squared minus 2xlb plus b squared. What is this? So let's say that Si is sum from L equals 0 to I minus 1 xi, and Qi is sum from L equals 0 to I minus 1 xi squared. Then B is simply as j minus Si over j minus I. And I can easily say that B squared this number of times is Sj minus Si over j minus I. And this is squared. Okay, let's go on. This is just sum of squares, so this is Qj minus Qi. Finally, this is minus 2 times sum times B. So minus 2 times sum times mean. Now you see that we subtract from this thing 2 times, instead of b, it is j minus I. And we subtract from this thing 2 times the same thing. So it is simply qj minus qi minus sj minus si squared over 2 over j minus I. So this is the cost of the segment. If we can calculate the prefix sums of x's and their squares, we will easily calculate this quite fast. So this is the first thing that we will do. So VL S, so we need const int n equals x dot size, and s of size n plus 1, q of size n plus 1, and we say that si plus 1 is si plus xi, and qi plus 1 is qi plus xi squared. Now we can calculate cost of a segment. And the cost of the segment equals QR minus QL plus SR minus SL times SR minus SL divided by R minus L, or multiplied by 1 point divided by R minus L. Okay? Does it make sense? It does not actually make sense, because what? So if I have a sum of such numbers, it becomes 5 billion. And 5 billion squared is unfortunately bigger than long. So I cannot allow myself to do it in long. So I have to do something like this. Okay, auto cost is calculated. Now it's a simple Well, it's a simple problem. Why is it a simple problem? Because now we need to solve this. Again, let's say that Pn is minimum cost. Pkn is minimum cost of Pki. If minimum cost of from 0 to I, if take k stations. Yeah? So first of all, we can calculate these costs for k equals 1. Sorry, my camera is broken, so I can try and fix it. Maybe it will, maybe I will succeed, but maybe I will break something else. Let's see, did I succeed? Yes, I succeeded. So minimum cost of from 0 to I if we take first k stations. So let's firstly calculate Pi. Actually, let's calculate P0, I think. Let's calculate P0. So P0 is 0, but P0 greater than 0 is plus infinity. So it is easier. Using Vd equals vector load, Vd dp of size n plus 1 filled with plus infinity. Actually, this is too small for a plus infinity. And if I just take one bus station, each thing becomes what? Something like xi squared. Yes? No, it actually it's fine. It's fine. It's 5 times 10 to the 14th power, so 10 to 18th power is definitely a plus infinity. And dp0 is 0. So this is our dynamics. However, this is the 0th dynamic, and I want to calculate the kth dynamic. For that, let's keep also vector dq size n plus 1. And we will do the following. We will k times change dp to dq and then swap them. Actually, let's swap them in the beginning. So we start with swapping dp and dq. So now dq contains the k minus first layer, and we need to calculate the kth layer. In the end, we return dp.back, I believe. Okay, how do we do it? Actually, we know that dp k I is minimum among all choices of j from 0 to I. Well, immediately we know that dp0 is 0. No, let's call it not I but ether, for example. And here I. So we need to choose any j from 0 to I. First of all, we need to take dp k minus 1 j plus dp plus costs from j to I. Great. The problem is we don't want to spend quadratic time, and now it is quadratic for this k and for this j. However, there is a fact which is called monotonicity of cut point on a prefix. Actually, it is true that, so let's say that cut ki equals minimum j such that dp k minus 1 j plus cost j I is same as dp ki. So this is the minimum j which can be put here to get and to obtain the minimum answer, the optimal answer. So actually, for each k, this function is non-decreasing. That means that we can divide and conquer. On the segment from 0 to on the segment from 1 to n. Okay, so we need to calculate the values of this function from 1 to n. How can we do it? Well, let's write a recursive function which takes the following. So let's write a recursive function. Auto recalc. What it takes? It takes the first number for which we want to calculate the dynamics, the last number for which we want to calculate the dynamics, the minimum possible cut point which is possible, min cut, the minimum number, number which is not possible. So let's call it cut L and cut R. Okay. To do that, let's also write another function which is called linear search. Do we already have linear search? No, we don't. So what does linear search do? It takes an index, it takes the bounds of the search, and it needs to return a pair of the cut point, which is int, and the objective function, which is float. Let's start with this easier function. We say that initially we try ans, which is simply cut L, and for example plus infinity. Let's go through all numbers. Cut point should be j, So here we need to calculate the cost of, actually we just need to apply this function. So dp previous, which is dqj, what's wrong with my camera? dqj plus cost ji plus cost ji. So let's like write, no, I want in other order. Float int, and here also in the other order. So we say that a possible answer is this number and j, and answer is assigned minimum of answer and possible answer, and in the end we return answer. Okay, we have written the linear search. Now let's write the recursive function. How do we calculate the recursive function? First of all, let's take the median. Let's take the median. L plus R, I said plus R over 2. Then we can calculate the optimum for it with linear search. So in point M, from cut L to cut R. It is important for two reasons. First of all, we can store this number in... actually we can stop. So if L equals R, we can return. If... First of all, we can take dp of M and say that now it is mans.x. This is the first reason. And the other reason is we can run this lambda recursively. So we can say that now we recalc from L to M and from cut L to minimum of cut R and 1 plus mans.y, and recalc from M plus 1 to R and from maximum of actually just like this, and from mans y to cut R. However, it cannot work like this because recalc cannot refer to recalc if we still don't know its type. So unfortunately, we'll have to include functional and define it as a function. No, not this one, but this one. As a function which takes 4 ints and returns void. Okay, this is called divide and conquer, and it works in log n time, because actually these recursive calls form a tree, and each level of a tree takes linear time. And there are, since we do it a balanced tree, we get a balanced tree, recursion tree. So the depth of the recursion is logarithm, And since on each level of the recursion we have the linear asymptotics, in total it is n log n. Now we can say that we need to recalc since instead of lambda we called it a function void int, now the syntax highlighter does not want to say me about the actual names of these variables. Okay, I see them. I can write them because I see them. So L is the minimum number for which we need to calculate dp. It is 1. Maximum number is n plus 1. Minimum possible cut point, actually, it should be less than j, and j should be less than I. It's interesting, but j should be less than I. Okay, in recalc, the minimum possible cut point is 0 always, and the maximum possible cut point is n. I don't know. Well, that's it. Now we need to test it. It didn't compile. Too few template arguments for a vector? Ah, it seems like it wasn't able to define a float. Well, it's not good. It's not good. Okay, let's define all 3 possible problems of such type. And it's always the same, actually. Okay, dq is all zeros, which is not correct. Ah, no, it is fine now. Ah, I need to go. Ah, oh my god. I need to only run it once. What, it didn't change anything? So, first things first, for a medium point m, which is what? Which is... yeah, I'm also in release. For a medium point which is 2, also n is not known. Maybe this. And okay, no. Ah, maybe because I don't use n here, so it doesn't know about n. It said that the best cut point is 0 with answer 9.50. No, it's not possible. It cannot be that big. Unless it can. But even so, this is not correct, because it should be like 7/3. What happened here? Why? Ah, for m equals 2. Okay, for m equals 2. So I take these 2 points, and I want to cover them with one segment. It's a little too big. Let's look into this cost function. So the cost function wants us to take q2 minus q0, which is 5. Ah, we need to subtract this, not to add this. Okay, now it's a bit smaller. Yeah, this is correct, this is correct. What about this one? Yeah, so we need to take 0.7/3. So it is 4/3 squared plus 1/3 squared. So let's write 1 minus 7/3 plus 2 minus 7/3 plus 4 minus 7/3. This is 69 plus 1/9 plus 25/9. In total, it is 42/9, which is 14/3, which is 4.666. Yeah, that's what we see. Okay, maybe it's fine. At least it works on sample. It works on sample definitely. Oh. Okay, I'll be back in a minute. Excellent. We got an accepted. However, it seems like it spends too much time. Yeah, because it is 1.4 seconds, and if I had 1.5 seconds, it would be a tail, and tail would be a disaster. Okay, we'll take that. We'll take that, especially because, like, I wrote the optimal solution, as far as I know. Optimal binary search tree. So let's consider the set of E1, E2, etc., En of different elements. We need to construct a binary search tree on these elements, but also for each element we know the frequency of taking this element. So we need to minimize this function where f of ei is the given number. Yeah, in this array it is given. And the second number is the number of edges between the root and this leaf. Not leaf. No, yeah, not leaf, I think. Yeah, not leaf. They are never leaves. Okay, and so it is called a static optimal binary search tree. Static because we know all the queries. If we didn't know all the queries in advance, then it would be a dynamic optimality. But there is hypothesis that the splay tree is dynamically optimal. Also, the second reason why it's called dynamic optimality, because splay tree modifies itself, and here we cannot modify our tree. Okay, we need to find the cost of optimal binary search tree. Let's go. So as usual, we need to write them in a segment. And what we need to do, we need to choose a root. Let's choose some vertex ek as a root. Actually, instead of 1 to n, first of all, it will be again from 0 to n minus 1. Secondly, let's take, as I said, let's take from L to R. Let's choose some root. E, J will be the root. What is the cost then? So dp L R is minimum among all j's from L to R. What do? We take this, we put it in the root. We put it in the root. Then after we've put it in the root, here we put the optimal tree of segment L j minus 1, and here we put the optimal tree for j plus 1 to R. What will be the cost then? First of all, it's just dp L j plus dp j plus 1 R. But after that, actually, 1 will be added to all these and to all these. Not 1, but the sum of costs. Not costs, but frequencies. So all frequencies from L to J minus 1 and sum of all frequencies from J plus 1 to R minus 1. Which is, to put it simple, let's call SI is sum of all frequencies from 0 to I minus 1. Then it is simply minimum, again, dp Lj plus dp J plus 1 R plus SR minus SL and minus Fj. So this is our function. Okay. How can we calculate it? Let's calculate it layer by layer. So let's draw a matrix. Yeah, and this dimension is L, and this dimension is R. We only consider segments in which R is greater than L, right? Right, yes. So we only consider this part of the matrix, because only here, where L is less than R, we can have some non-trivial results. So how do we calculate a cell? We can calculate it in linear time. So let's try and do it. So we have several tests. So now actually I hope that the number of tests is at most 1 billion. So what? We read n. And then we read the frequencies. And then we write the answer of f. Okay. LL find answer of VIF. Actually const VIF. So let's start with the prefix sums. Actually, we know that the prefix sums are all at most 500,000. So let's put them in VI. Okay, now we need to calculate this dynamic. Our aim is dp 0 0 n, yeah. But instead actually of dp, we will calculate the cut points. We will calculate the cut points, optimal cut points. Yeah, because if we know, again, cut point is such number j that this number is optimized. Because if we know the cut point, then we can substitute it in this formula and get the answer. Again, let's fix the difference between R and L. And now this is one-dimensional array. So vi cut is of size. Let me think of which size. Size n plus 1. And let's assume that it contains just I. And then, so it is the array for differences 0. And now we need to find the array for difference 1, 2, 3, etc. n. Int d, which is difference from 1 to n plus d. So assume that vector cut contains the difference for d minus 1. Let's also have prev cut. As usual, cut.swap prev cut. Then we say that cut dot resize what? So if we have some number d, then we need to resize to n minus d plus 1, I think. Now what do? We need to go through all numbers from L equals 0 to L less than something. Yeah, we want to look at the segment. We want L plus D to be at most n. So something like this. Now R equals L plus D. And we need to find the optimum for segment from R to L. Now let's iterate over all possible cut points. So let's say that our current answer is 1e18. And we iterate over all possible cut points which are from L to R. So what do we try? Current answer is, as I said, I need also to know dp actually. Yeah, I need to know dp. So let's also know dp. So I have dp of size n plus 1. Yeah. And vi prev dp. So I need cut.swap prev cut, dp.swap prev dp, cut.resize this, prev dp.resize this. Okay, and here in the end I will say that dp. Okay, let's store it where it belongs. So not ans equals 1e19, but dp l equals 1e18. So what is current ans? Current ans is prev dp. Actually I need to know all dps. Yeah, I need to know all dps always. So I need quadratic memory. Can I afford quadratic memory? So n is at most 5,000, so I will need 25 million ints. Int is 4 bytes, so I will need 100 bytes. So I can, I can store all of them. Let's do it. Yeah, so I will not do this. Instead, I will have VVI DP of size n plus 1 and VI n plus 1. Actually, 1E18 is a little bit harsh. It should be 1E9 at most. Yeah? Or not? It can be 5,000 times 5,000 times 100 over 2. So 5,000 times 5,000, 25 million. If we multiply by 100, it becomes 2.5 billion, but then we divide by 2 and it's 1.25 billion. So we can take infinity as 2 billions, 2 and 9. So dp LR is 2 and 9. So no pref dp here, of course. Okay, what is pref dp? Pref dp is just dp L j plus dp j plus 1r plus sr minus sl minus fj. Okay, if currents is less than dplr, then dplr is currents and cut L is j. Okay. Must return value. So the value should be in dp zero n. 0, 20, 20, 63. Yes, it's correct. However, if I try this, it will be slow. It will be slow because it is cubic asymptotics. This is O of n, this is again O of n, and this is again O of n. Actually, we can make use of our pref cuts, and instead of going from L to R here, we can go between the pref cuts. Namely, we can go here from maximum of L and pref cut of L, and here minimum of R and 1 plus pref cut of L plus 1. And actually it still works, but now it's fast. Yeah, let's check that. I see, actually I use C++ 14. Maybe I need to use 64-bit C++. Maybe I just need 64-bit C++. Let's check if this works faster with 64-bit C++. 4 times faster. Why am I trying to submit in C++14? Because I am masochist. Okay, problem D. Pizza delivery. This is... It's not a bug? What's happening? Why is it looking like this? It's very bad. Okay. Time limit per test 2 seconds. Memory limit per test 512 megabytes. Flatland is one-dimensional. It means that each point has only one coordinate. Everybody in Flatland loves pizza. There are n pizzerias and n consumers. The ith pizzeria is located at point Si and ith consumer is located on point Ci. No two pizzerias share the same coordinate, but 2 consumers can share the coordinate with the pizzeria or other consumers. Every consumer wants to own a pizza and spend as little money as possible. The ith pizzeria sells pizza at a certain price P. Shipping costs square of distance. Okay. Fortunately, some consumers don't like some pizzerias, so they won't order pizza from there. Specifically, the ith consumer won't order pizza from pizzerias D1, DI1, etc. DIKI. For each consumer, find the money they will spend. What? Sorry, but what? Ah, it's one dimensional. Okay, it's one. If one dimensional, it's kinda okay. Well, it's hard. I don't know what to do here. So we have n pizzerias and m consumers. They are points on the line. Both these numbers are quite big, 200,000. Every consumer wants to order a pizza and spend as little money as possible. The ith pizzeria sells pizza at a certain price pi. Okay. So let's first of all forget about the restrictions. So each consumer likes each pizza. In this case, each consumer is minimizing the function pi plus xi minus cj squared. How to minimize such a function? Well, it's a parabola and we need to minimize several parabolas. Well, Convex Hull Trick relies on the fact that... Relies on which fact? Relies on the fact that each two functions intersect at maximum one point. However, in this case, any two functions can intersect in 2 points, and it immediately becomes infinitely worse. Actually, the nice thing is the following. The nice thing is we can from all, so we want to okay, let's find the maximum possible money that we will need. Maximum possible money that we will need. So P is 1 billion, 10 to the 9. SI CI is 10 to the 9. Difference between 2 CI and SI is 10 to the 9. The square of difference is 10 to the 18th power. So the maximum possible price is 10 to the 18 plus 10 to the 9. However, okay, let's add a fake pizzeria which is at point 0, which is always available. Everyone likes this pizza, but its price is 10 to the 18th power. Then everyone can buy this pizza. Now let's subtract its price from everything else. So we have a pizza of cost x0 plus infinity. Let's call infinity c. X squared plus c. So this is the cost of my pizza. I have made a pizza, but it is made of brick and it is infinitely expensive. Instead of minimizing this function, let's minimize this function. Oh no, I don't want to call it C, let's call it P, grade P. So we are subtracting x squared actually we can just always subtract x squared because x squared does not nothing depends on x squared. Okay, we get minimum of pi plus xi squared minimum over all i's minus 2xici cj and plus cj squared, but cj squared we can put it here because nothing depends on it. Okay, now it is a linear function, so let's say that f I of x is pi plus xi squared minus 2xi times x. So this is cj squared plus minimum over all i's Fi of Cj. Okay, this is now definitely a convex hull trick. However, it's not that easy, because instead of simply a convex hull trick, we have a problem with this thing. So, the ith consumer won't order pizza from pizzerias di1, etc. di-ki. And convex hull trick is unable to ban some of the lines. So if you add line, then it works. If you don't add the line, then it doesn't work. Okay, problem D is convex hull trick plus something strange. So we will take it later. For now, let's solve problem E, I think. So we live in some vertex, and in each vertex we have AI and BI. Actually, it will be easier for me to draw BI at the top and AI at the bottom. So BI is like entering gate and AI is exiting gate. So when I can jump from a vertex to any vertex in its subtree, and I need to trigger its exiting gate and trigger the entering gate of the vertex in the subtree. Yeah, so we have here bj, aj, and I combine these numbers. The total cost of a path formed by one or more jumps is sum of costs of individual jumps. For every node, calculate the minimum total cost to reach any leaf from that node. Pay attention that root can never be leaf, even if it has degree 1. Wow, it's awful. Actually, it's not awful. It is quite bad. Okay, first of all, let's make a DFS traverse of our tree. Let's list all our vertices in DFS order. Then for each vertex, right after it, there is its subtree listed. Yeah? And for each vertex, we can store two numbers. How much dp I itself, so it is I and this is j, so dpj. How much does it cost to get from this vertex to the leaf, to any leaf? And actually the other number is bj of this vertex. And so the answer is minimum of bj times ai plus dpj on this segment. And all these things are just linear functions. And we can store them in a Convex Hull Trick. So now we have the following problem. What? Yeah, we have the following problem. You need to choose so we need to make a Convex Hull Trick structure, which is mergeable, yeah, because in the end we want to combine I with all its children. We can do it. Oh my god. Oh my god. Yeah, we can do it. We can do it with Li-Chao. And the total asymptotics will be n log squared. Are we n log squared and you give 0.3 seconds. Well, 0.3 seconds is enough, actually, for n log squared, because log squared is 400. 400 times 10 to the 5 is 40 million. 40 million is enough. For 40 million, 0.3 seconds is enough. Definitely. So if we do everything with enough accuracy, it should be fine. Oh, Li-Chao Tree. It's not really good. Or is it? No, it Is it good or not? So the problem is we want to store Li-Chao Tree. But not with really many lines. Well, we can just make... No, I don't get it. So we need... The only problem now is to store Li-Chao Tree. with memory linear in number of lines. Okay. So I need a Li-Chao tree which size is linear in number of lines. To do that, I can store it explicitly. Yeah, I can store it explicitly. In this case, it will be linear. But it is bad. It's really bad. However, even though it is really awful, it still kinda works. Still kinda works. Okay, let's try. Let's try it. It will be really bad, but we will try it. I already understand that it will get ML, TL, and everything in between. Okay. So again, we have a DFS. DFS stores a Li-Chao tree. It's not good. It's not good. No, it's not good. Okay. So Li-Chao Tree node. This is what we need. What does it store? It stores left child and right child. Okay, it stores them, left and right child. And also it should store a linear function. Which is int k and LLB. Great. Now we need to push something in a node. How do we do that? How do we push something in a node? Let's write a function void push and we push some other linear function. Linear function f can also be infinitely big. So how do we make it infinitely big? To make it infinitely big, let's say that we have const ll inf equals 118, and to make a function infinitely big, we just put infinity in b. Let's just write it like this. So how do we push? And k equals 0, for example. How do we push a new linear function? Okay, first of all, if g is infinite, then return. If f is let's do it like this. If f is infinite or g is not infinite and when we push, we also want to know the breaking point. Yeah, so let m be the breaking point. Yeah, let's make it simple, because I don't want to feel idiotic. So if g dot b is infinity, then return. Also, if f dot b equals infinity, then f equals g and also return. Now they are both not infinite. Let's also compare them in point m. If f of m is less than g of m, is greater than g of m, let's swap f and g. If f.k equals g.k, then return. Now we need to push it further. How do we push it further? How do we push it further? We need to understand, so if f.k is greater than g.k, this means that on plus infinity f is greater, then so we need to push g to the right. We need to also make a static function. Static this push node const linear g constant f. And we will run, okay, let's call it static push. We need to make static, we need to say that r equals static push of rj well, actually we need to know the segment. We need to know the segment. So when we go to the right, it is also if r minus l is 1, at most 1, then we also return. We don't want to push it further. Okay, at this point we say that r equals static push let's call them L big and R big. Capital R. Capital R is capital R G, and now we need to give it a segment. So on the right hand, segment is from m plus 1 to r. Else L is static push, L, G, L, M. So what does static push? If ND is existent node, if ND exists, then we simply push into it. Yes, so we say ND push everything same, L, G, L, R. Else ND equals something, and then we will say return ND. Yes, here we say that ND is new Li-Chao Tree node. Also, we need to fill it. So we need to say so we have filled it. It fills with null pair, and here it fills with 0inf. And we need to say that we push G to F. And that's it. Actually, we can make a constructor okay, we have made the constructor, and here we can just put G. So now it becomes shorter. Well, we have written Li-Chao Tree. Yeah, also we'll need to actually we'll need to make a destructor. How do we make a destructor? So if L, then delete L. If R, then delete R. That's it. This is actually sad that I'm doing this. But okay. So let's make a VL ans of constant n equals e dot size plus 1. Then we say VL ans of size n and return what is the root. Root is at node 1. Let's make it 1 indexed. Okay, return what? Return nonce. Before that, we need to run DFS from vertex 0. DFS will return what? A pointer to a Li-Chao tree. Also, we'll need a V, B, and V. Okay. DFS 0 and VG. Here we say that NV is true, it's false. Also we'll pass sans. Yeah, we will pass ans. So what is our goal? Our goal actually, let's pass two things. Let's pass pair of this thing and the size of subtree. We will pass the size of subtree. Yes, so the bigger the subtree, the bigger this number. Okay, what do we do here inside the DFS? We will store all these pairs. Okay, vector pair thing. Children. So here we store all our functions. Also, let's say that we have something like pair of this thing and this thing, which is called main child. And initially it is null ptr and zero. So if not easy to 2, let's push it to children. Children.push back DFS of 2nv giants. If children.back.y is greater than main child.y, then swap main child and children.back. Okay, now we have the main child and some children. Now we want to write a function which iterates over all functions in the tree and adds them in the main tree. So main child consists of some functions. We need to make a union of all these functions and make it a main child. Let's go. How do we do it? How do we do it? Actually, let's write one more function in Li-Chao tree. Static Li-Chao tree, no, static ll static find min in Li-Chao tree node nd const int x this and this. How do we do? So if nd, then return and D find mean of XLR. Else return infinity. Now we need to write a function find mean of X L R. And this is pretty straightforward. So first of all, we take our linear function. Okay, so what do we do? LL ans is f of x. Okay, and then if x is great, also constant m equals L plus R over 2. So if x is greater than m, then answer is minimum of funds and static find mean of right child XLR. Else answer minimum funds and static find mean of left X, not XLR but XLM, and here X m plus 1R. And then return nuns. That's it. We can also add this, but it doesn't change anything. We can remove it, yeah. Nice. Also, let's make a constant L and R, which are const int global L equals minus 100,000 and global R equals 100,001. This will be useful later. Now we write a function which takes a linear function What does it do? It simply adds this function to main child. So we say we say that main child dot x equals Li-Chao Tree node static push of main child dot x line line global L global R. That's it. That's the function. Okay, why is it important? Because we will write a visitor. So how do we visit? So we get a visitor. So first of all, we visit it with our function f. Then if we have a left child, we also run a visitor for the left child, and if we have a right child, then run it for the right child. And so actually we just need to add all children to our main child. So for const auto p from children, first of all we say main child y plus equals p dot y, p dot x. Okay, if p dot x, then p dot x, please visit all my children. All my lines. That's not it actually. Why not? That's not it? Because after that I need to delete my child. So I need to delete p dot x. Then I return main child. And here I say plus plus main child dot y. That's also not it, because before that I need to calculate dp and I need to add a function. So let's firstly add a function. Assume that we have calculated the dp. Then we need to find this function. Yeah, which is bj and dp. Wait, b and dp. So let's also pass a and b. So we need to static push what? A new function. Main child x. Then a new function which is what? New function will be bi and dpi. This is dp. First of all, bi, bv, and dp. And finally, L and R, which is GL and GR. So this is easy. The hard part is to calculate this dp, but actually it's also not very hard. We need to minimize this thing when we put AI. So dp is Li-Chao Tree node. Actually it's funny. It's funny because so if main child dot x, then dp equals this a static find min of main. We don't need static. find mean in point AB. Else it is 0. I can just write it right here. Okay, we have done it. So the code is written. Everything is ready. All zeros, which is not good. Maybe because I don't know why. I don't know why. I feel like we will. Okay, let's make a more simple test. 2, 1, 2. What is here? Here we need to write A's and B's. For example, 1, 1, 1, 1. Still 0, 0. No, it is not good. We will fix that. Okay, we need to static push something. Let's see how it happens. So we have a function x. If nd push, else nd equals new Li-Chao tree of g, return nd. Okay, it returned. So now in main child, it should be that this is 1 and this is, yeah, this is totally correct. Okay, we pushed it back to the children. If children back y is greater than male child y. Actually, I don't want it like this. Let me fix that. So if not main child dot x, then I assign main child equals I see. Okay, if children dot back dot x is not true, then children dot pop back. This will be nicer. Well, does it help? Not really. Okay, we need to find minimum. Find minimum is 1 actually. I didn't return anything. What? I need to... What do I need to do? I need to store it in the ans. So I need to say ans. So ans is initially 0, so I don't need to check change anything. I just need to write like this. And then I need to put DPV here. Okay. Now it's 1, 0, 10, 50, 0. Well, it is definitely a tail. However, maybe it's not. I spent an hour. Wrong answer? Wrong answer is impossible. I cannot have wrong answer. No. No. No, it is impossible. It is impossible, no. No. It can't be. I can write like this. I'll speed it up a little bit. Hmm. Let's look at how I push it. Okay, actually, static push also should be changed. So if r minus l is 0, I don't want to do anything. If r minus l equals 0, I want to return null ptr. Okay, if fk is greater than gk, this implies what? It implies that on the right side, I am becoming bigger. So g is maybe optimum. Else on the left side, it is maybe optimum. Wrong answer on test 6. But why? Let's, I don't know. I really don't know. It might be that I don't know how to write Li-Chao Tree, but I'm not sure because everything was quite straightforward, wasn't it? Okay, let's try and do something. For example, let's make the following tree. The following tree. Following tree is this vertex, this vertex, this vertex, this vertex, this vertex. Then something like this, something like this, and overall a vertex -1, 7. So the optimal thing for this vertex is of course to pair up with this immediately. However, if this was not added firstly in this tree and then in this tree, then it won't work. Okay, let's check. We have 8 vertices. Let's list all A's. A's are the lower numbers. Let me call them 1, 2, 3, 4, 5, 6, 7, 8. -1, 3, 1. 1, 1. 1, 2, 1. Then A's. Or B's. 7, 9, 6. 5, 4. 3, 5, 1000. Then I need to list all the edges of my tree, which is easy. 1, 2, 3, 4, 5. 1, 7, 7, 6, 6, 8. 7, 8. So it should be 1000. Ah, yes, it is 1000. For the vertex 2, it is 12. Because the best thing is to pair up with this vertex. And this it's 6. Okay, let's change test a bit and say that it is 2000 and this is 9. And this is 900. Okay, let's change the test. So first of all, 6th vertex is now 2000. Secondly, the second vertex is now 900. This is 9. Second vertex is 900. Okay, what now? Now it's 36. No, it's impossible. Why is it 36? Ah, it's 94. Okay, let's disallow it. I don't want it. Now 2045. 2045 is correct because it is 45 and this is 2000. So, yes, it works. And why on earth it doesn't work in the Codiforces, I don't know. I won't say that because they have wrong tests, because this is simply ridiculous. But I am not happy about that. Wrong answer, test 6. Okay, the question. Is it enough to put in this tree only functions from the Li-Chao tree, not every function? The answer is yes, of course. If I need any function and it disappeared from the Li-Chao tree, it means that it is never optimal. And I don't need it. Okay, I have two ideas. First idea is to make a stress testing. So I generate a tree, and for each also I need to delete the answer, of course. So I need delete dfs.x. Yeah, it is important. Because else it's memory leakage, and I don't want that. Okay, let's make a stress test. Find dance low. How to find dance slow? Same thing here. Same thing here. But let's start with infinity. DFS slow of 0. Okay, I also want a stack. So 0. Actually, we can make DFS with this stack. DFS P and V. G. Ans AB. DFS slow. We say that not visited. But first of all, V is P dot back. I say that NVV is false. Or int2 in GV if NV2 div then P dot pushback to DFS slow to NVM GANCB P and P dot pop back. And after that, we need to update the answer for all our P's. So for int Q in P, if Q is not P, we need to say that answer Q is minimum unsecure and product of AQ times BV plus answer V. Okay, now we need to write a stress. While true. So we need to make a test, which consists, and to make test we need to make struct test. What does test consist of? It consists of A, B, and E. So as we say that test equals again test. Then we say that real correctance is find and slow of test.a, test.b, test.p, and find ans hour. And if correct ans does not equal past ans, we need to print both of them. So we print n, then we print a and b. B, then the edges. Okay. How do we generate a test? Quite easy. Generate a test. We need, first of all, we need to choose an n. Chose. Then we need to create a test. ta.resize n, tb resize n, and we need to say that tai equals uid minus this rng, and b is also minus this is an rng. Okay, finally we need to construct a tree. How do you construct a tree? to construct a tree, we will do the following. We will create, first of all, a clumsy tree, and then we will renumerate it. We say t.e.resize resize n-1, and in this tree we say that te is connecting I plus 1 with uid 0i rng. If uid 01 rng, we need to swap tei.x and tei.y. Finally, we need to shuffle t.begin and te.end. And not only that, why we don't know shuffle? Because RNG. Not only that, we also need the vector of renumeration. We also need to shuffle this. And after that, we need to say that TEI is renumeration of TEI and of X and of Y. It created some tests. Let's go. No, it shouldn't be okay. Because my leaves are incorrect. Okay, let's fix leaves. In the leaf, the answer is already 0. Okay, how do I do it? I need to take... Let's calculate children just. And if not children, then ans v is 0. Okay, now it can't find anything. So maybe we'll need to increase this. Now it immediately finds something. Already for 4? So for 3 nothing, but for 4 it finds something. Let me think. Yeah, first of all, I want to add 1 here. Secondly, I want to try taking maximum 3 here, so it becomes smaller. It still found something. What about 1? So that it's most as easy as possible. Okay, so the tree is 1 4 4 3 3 2. So I'm bamboo. Yeah. So the correct answer is to jump from -1 to 2. So it becomes -2. Ah, you cannot. Again, 1 4 3 2. So this. Ah, I see. From 1 to 4, then from 4 to 3, and from 3 to 2. Okay, it makes sense that it should be -3, but for some reason I didn't find -3. Found only -2. Let's try to find -3 as well. DFS. Okay, return main child. Let's look at the main child. Main children. Okay, starting with 2. So this is simply a function x. No, it should be 2x. So there is just a function. I said there is just a function 2x, right? Yes. Then there is a function constant -2, and in its left child there is function 2x. Is it correct? It sounds like it is correct, yeah, because... Well, because... You know... So in point 2 it is 2x, correct? But in point 3... Yeah, what if you jump in point 3? You nullify everything that you got, and then you get -2. Yes. Yes, actually this is correct. let's go next. So now main child is also this function. Okay, let's draw our functions. I want to draw them. So function number 2 is 2x. So this is 2. Function number 3 is minus 2. Also, we have function number 4. What do we do in function number 4? It can choose either jumping here and getting 0, or jumping here and getting minus 2. And it chooses minus 2. So it is like x minus 2. Yeah? X minus 2? Yeah, x minus 2. There should be a function x minus 2. Oh, sorry, not like this. Like maybe like this. X minus 2. And we need to store all these functions. They all three can be minima. Okay. So what? So we have a tree. In here we have just minus 2. Okay, we don't have a right child for some reason. Actually, it should be stored in the right child, because in the right child... Ah, this is optimum in right child. Yeah, I see. So somewhere in the left child, the optimum should be the black function, so minus 2x. So here it should be 2x. And then in its right child, it should be x minus 2. Yeah, everything is correct. So far, 100% success. But then something bad happens. Okay. Now we're trying to substitute AV, which is minus 1, to one of these functions. Wait, minus 1? Okay, so this function, green function, it is optimal in this point. Yeah, so it is simply optimal in this point. Ah, no, it's not optimal at this point. Okay, let's see how it works. So we know that m is 0. X is smaller than m, so we go to the left child. What did I do? So if x is greater than m, for some reason I go to left indices? Oh, it's harsh. And now it should work. It now becomes easy peasy lemon squeezy -3. Yeah. Who would think? I'm so dumb. Well, let's continue our stress. It found so much interesting. Now let's take 7, I don't know, and 7. And actually 100,000. Nothing? What about 70? One megabyte even for 70? What about 700? I think we have a leakage. Also, I want to... slow test is maybe slow, yeah. Well, it's not because it's n log n also. My tests are random. Okay, so a lot of tests here. About 7,000. Still quite many, but it is slow. It's about 70,000. Well, it's bad, but not that bad. Okay. Okay, whatever. And do I get it right that if I want to send it in 32 bits, it is too slow? I think it might be. No, it might be even faster actually, because... No, it's not faster. But yeah, it is... It is accepted for some reason. Okay, we'll take that. we still have a lot of problems to solve. It looks pitiful that I spent an hour on this problem and then another almost an hour on this problem. So how can I solve again? So I have a problem. Convex Hull Trick, everything as usual, but not so easy, because Convex Hull Trick, which is able to ignore lines sometimes. When it wants to ignore lines, it ignores lines. How can I do that? Ah, maybe it's square root decomposition. So I can solve it in n log n square root of n. How do I do it? I divide all pieces in square root of n areas. In each area, if all pizzas are allowed, I use convex hull. If not all pieces are allowed, I do them one by one. Okay, actually, let's write what I expect to do. So I expect to divide all P series into A groups of B series. So each query is, first of all, I do every group independently. In each group, either everything is fast, and I do it in log B time, or it is slow and I need to do it one by one. But yeah, so let's assume that I always spend A log B. So number of queries times A log B. Yeah, okay. But also for let's call this number sum of ki's k large. For each k large, I will have to spend B. So qa log B plus kb. What do we say then? We say that actually B is n over A. Okay, A is n over B. First of all, here I can put log n, and here I can put n over A. n over B, yeah. Let's take derivative B, so k plus minus q times n over b squared log n equals 0. This means that b squared k equals q n log n. Q n log n? What? Q and log n is too slow. What's happening? Ah, okay. So now I say that b squared is q and log n over k. And finally, b is square root of q n log n over k. And this thing works in square root of k q n log n. Oh my god. Oh my god. So can I afford myself this? Let's calculate. So log n, for example, let's just take 2 times logarithm. Okay, q. What is q? Q is number of consumers. Number of consumers is 2e5. Times q, times k. K is 4e5. Number of pizzerias is also 2e5. And log n is something like 40. Okay, let's take a square root. So square root of, it's 10 to the 7th power times what? What do we have here? We have here 2 times 10 times, actually no, it's 10 to the 8 if I remove also this 0 times 8. So it's, what? So if I do like this, I must probably lose. Well, I can try, but I probably lose. I don't want to lose. Well, we can try because there were things which were worse. So Petty and triangle and rectangles. Let's copy this. Yeah, because it contains a convex hull trick. Now let's modify it for problem D. So we read n and m. Then we read coordinates and prices of pizza. So, okay, let's make a funny structure for that. So coordinate S and P. Actually, why do I do it? I can store them in VIs. Then we store ith consumer's coordinates and pizzeria where he won't order pizza. 2 seconds. It will be so slow. I hate this problem. So VICM and VVI DM. Okay, and then we need to find ans. Then VL ans is find ans of SPCD and we print it. Great. Find ans SPCD. Okay. Let's go. Find ans VL. So we'll do it for customers one by one. Font in M is c.size. So what do we do here? Actually, so we will have all P series. We need to calculate B actually, first of all. B is this strange square root. Okay, let's calculate it somehow. Let's calculate it somehow. So, for example, how can we calculate it? We need to calculate k. Let's start with k. Okay, we calculated k. Then we will need to take... Okay, we will need to take q, which is number of customers, which is m actually. So m times k times n log n times n times log n while this is less than n plus l. M and L divided by Q divided by K. Something like this. Then we need to take square root. Okay, B is the size of block. So if B is maximum of B and 1, now we have blocks of size B. Is it okay actually? What if K is very big and N and Q is very small? It's okay. It will be okay in this case. Okay, then we need to say that int a is n plus b minus 1 divided by b. So I have a blocks. For each of them, I need to make a convex hull trick. So I need vector convex hull trick. How do I fill it? So let's come again. So what do? I have a pizzeria. I have a pizzeria. So the answer is pi plus xi minus cj squared. We remember that actually it is pi, it is cj plus minimum pi plus 2x cj squared. So pi plus xi squared is a function, and 2xi is linear term. So I need to sort them by xi. Yeah, I need to sort them by xi. I can do it. Well, I can do it. So let's take vector linear. I need to sort them in decreasing order of xi. It is minus. So actually I need to sort them, Okay, whatever. Vector linear L. So for int j is I times a, I times b. J is less than minimum of n and I plus 1 times b plus j. L dot pushback what? Minus 2xi xi is in place of the p series, so it's sj. And here we have pj plus sj squared. Okay, and then I need to sort them in decreasing order. I want L1 to be before L2 if L1.k is greater than L2.k, and I sort them in this way. Okay, after I've sorted them, I can put them in Convex Hull Trick. So I say that for const linear M from L, okay, O from L, Convex Hull Trick I dot add O. Okay, we want to go through all blocks. In each block, if there are no bad cafes, bad pizzerias, then we just take minimum. If there is a bad cafe, then we just go through all cafes in this area. How can we do that? I see actually how we can do that. We need to take VB band Sn. Okay, so when we enter a customer, first of all, we ban all cafes which are banned. So const so, like just for int j from di. Also, let's say vi banned in block A. Let's go. So we need to ban the jth cafe, jth pizzeria. How to ban jth pizzeria? First of all, we need to say that it is banned. Also, we need to say that it is banned in block. Okay, now we need to go through all blocks. So int b equals 0, b less than a plus b. Let's take this block. So if banned in block b, then we have to go through all this block. Else, we will look into the convex hull trick. So we say that ans I is minimum of ans I, and convex hull trick b dot find mean of ci. Okay, what if it is banned in block? Yeah, so there is something banned in this block. Let's find out the numbers. Actually, it's something that I also needed to do here. So let's say int L equals I times B, R equals this minimum. The same thing needs to be done here. So we iterate over all numbers in this block, and we say that ans I is minimum. So if not banned j, then ans I is minimum of ans I and the corresponding linear function. We will add xi squared in the end. Let's assume that we add xi squared in the end. Or not. Okay, let's add it immediately. Let's add it immediately because it makes sense. So I need to put this person into jth pizzeria. How do I do it? It is ej plus ci minus sj squared. Okay. Okay. We are done. 11:34:13. Okay, since I don't want to debug it, let's try to submit and get our TL or ML or everything that you like. Relation error? Because of what? SQRT was not declared in the scope. Well, actually you don't. Okay, never mind. Let it be. I don't even know what to say and what to think. WA2? Okay, first of all, we will look into our solution. Ah, I remember what I need. I need to unban everything that was banned. Yeah. I need to unban everything that was banned. Still wrong answer, test 2. Okay, let's make a stress, because I so like making stresses. Let's actually indicate time. So let's remember time. 3:21 night AM. How fast can I make a stress? So this is easy, while true is also easy. So test t is n test, then what is the answer? VL correct answer is find ans slow t.s t.p t.c t.d, and fast ans is find ans. If correct answer is not fast answer, then we will need to print it. We need to print it. How do we print it? In the end we will return actually. How do we print it? We need to print n and m, which is size of s and size of c. Okay, let's make the structure test. So it's vi s, p, c, and vi d. So okay, we printed this. Then we need to print n lines with s and p. Then we need to print m lines print tci td I dot size, and for int j from tdi print space and k plus 1, and that's it. Then I need to say that wrong is a fast ans and right is correct ans. Then we need to write these two functions. Both of them are quite easier. So val find dance slow. How is written? How is it written? So here we need to do the following. We need to say that will be allowed of size n. True. Then we need to go through all these pizzas and ban them. For int j from di, allowed j is false. For int j0, j less than plus plus j, if allowed j ans I is minimum of ans I and this. So j plus sj minus ci minus times sj minus ci and return nonce. Okay, and the only thing left is to get test. How do I generate a test? So I need to generate n and m. N will be from 1 to n, and m will be uid from 1 to n RNG. Okay. I will allow the same pizza be in the same place. It's fine in my opinion. So t dot c dot s dot resize n, t dot p dot resize n, t dot what? T dot c dot resize n m and t dot d dot resize m. Okay. Let's go. First of all, let's put pizzerias. So I need to say that t.si is uid from 0 to x RNG, and t.pi is uid from 1 to p of RNG. Then we need to fill consumers. T.ci is uid 0x of RNG, and t dot. Then we need to choose number k from 0 to n minus 1 RNG. Need to say that t dot d dot resize k, then vi h t dot d resize, okay, n j0 j less than plus j, t dot d j equals j, t dot dij, shuffle t dot di dot begin, and t.di dot lamp and t.di dot resize v and return t. Let's see what it says. So I spent 9 minutes. Okay. Okay, now it's 10 minutes. Okay, it failed. Why did it fail? I need to resize, but I resized. TD is resize M, and TDI should be resized N. Why? C dot size. C dot size. Well, it actually found something. What? It actually found something. Why did it happen? Well, it's so obviously incorrect. So correct answer is 2, 30, and 5. I am not impressed by this fact. Let's put it after solve tests. I don't want it now. Okay, so I is 1, for example. I is equal to 1. Band is false. And then second and third are bound, yeah. And B is what? B is 2. So actually, all blocks are banned. Yeah. And here I needed to write B instead of I. so that it would be correct. Right? Are there errors? No. Okay, let's make it bigger. But still no errors so far. Now the only error will be tail, I suppose. Answer test 2. What's happening? If from answer test 2, it means that I even don't know what to think. Okay, let's try to find answer slow in this case. Maybe it will give us also VR2 or VR2. It's also VR2, so my find ans slow is incorrect. And then I definitely don't understand the... So, there are n pizzerias and n consumers. And first of all, we read n and m. Then we read n lines with S and P. All numbers are less than 1 billion, at most 1 billion. S and P, n lines with S and P. Then, next m lines have firstly Ci, then Ki, then all Di's. over it CI, KI, and all DIs. Maybe the maximum possible answer. Maximum possible answer is greater than. It's infinity is 2e18, not 1. It is stupid. Yeah. Okay, it happens. It happens. Now what we need to do is put here find dance and get our tail. Accepted? In almost 2 seconds. Who am I to disagree? Problem F. Crayfish. What is view nook? A bird? A plant. So, Charles Darwin caught several crabs. He has n crabs. A ith crab is aggressive with level of aggression AI. Also, Darwin has k aquariums in which he will put the crabs. He decided to put first T1 crabs in the first aquarium, second T2 crabs in the second aquarium, etc. plus TK crabs in the last aquarium. Crabs have feelings. Okay. Okay, it seems like it is also optimization on prefix. Maybe not, but let's see. Monotonicity of cut point on prefix. So, how many aquariums are there? There are k aquariums. And k is big actually. So if k is big, then I'm supposed to make 1D optimization, which I don't remember. Well, at least there is a simple quadratic dynamic to stress with. Okay, what am I supposed to do? Let's already make stress, okay? So what's test? Test is k and a vector of numbers, actually. That's it. So test is k and a vector of numbers. So gem test is really simple. To generate a test, we just need to do the following. So AI is TAI is UID of 1A RNG return team. So stress is as follows. So we find and slow of T dot A and T dot K and find dance correct. And actually it's just long. Fast dance is find dance TATK, and if they're different, we print T A size and TK. Yeah, then we say that wrong is fast dance and right is low ones. Correct ones. And return. Okay. Gen test, solve tests. Let's write this part, because this is also very easy. We need to read N and K, CVI AN, that's it. Okay, find dance, slow, and finance, simply find dance. These are our two functions. Okay, let's start with slow. How to find dance slow? We need to make a DP. Okay, so what is our DP? So each crab, what does each crab feel? Each crab feels sum of AIs for all other crabs. So in our segment, we just have sum from I equals L to R minus 1. We have sum of J is not equal to I and J from L to R minus 1, A, J. And actually it's simply SR minus SL times R minus L minus 1. Oh my god. Oh my god. So, that said, again, dp0, 0 is 0, dp0 greater than 0 is infinity, and dp k0 is 0, and dp ki is minimum over all j from 0 to I. Dpk minus 1 j plus what? Oh, plus I wanted to say plus si minus sj j I minus j minus 1, I guess. Okay, let's calculate it in cubic time. So we say that we have dp of size n plus 1 and infinity. Actually, yeah, long. What is the maximum possible level? If we put them all in one aquarium, it's something like n times sum of AIs. So n squared times AI. N squared times AI is 10 to the 17th, so 10 to 18 is fine. Infinity, dp 0, 0, viq n plus 1. Then we make k iterations. We go from 0 to to n. We say that dp dot slope dq. So now dq is the old dynamics and dp is the new dynamics. We say that dp 0, 0 for int I equal 1 to n. We say that dp I is infinity for int j is from 0 to I. We say that dp I is minimum of dpi and dq j plus si minus sj times I minus v minus 1. dp should be vl return dp dot back minimum of s. We need to calculate s. So vl s of 7 plus 1. Yeah. Let's check these two tests. 32, 37. Yes. Okay, fine. I can just submit it and get TL, but I will not. It's stupid. It's now n cubed and I need n log n. Well. 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 What? Okay, that's n cubed to n log n. Are you serious? Okay, let's well, I have a problem because it seems that even if I make this optimization, it's still n squared log n, which is not what I want. Maybe this is because it is lambda optimization. Ah, this is lambda optimization, not 1D, 1D. Okay, let's learn because I... Oh my god. Let's say that we can use as many aquariums as we want. Let's say that we use as many aquariums as we want, but for one extra aquarium we get a lambda fine. In this case, so dp, we can just say that dp I is minimum over j in 0 I dp j we need to combine 1D 1D and lambda. Oh my god, it's not what I want to do. Okay, plus lambda and plus s I minus sj I minus j minus 1. Okay, fine, we have this optimization problem. Okay, these are two separate things. Let's work with them separately. Okay? So first of all, we need to choose lambda. Which lambda is... So if I take lambda equals 0, then we always just take each crab in its own aquarium. If we take lambda equals a lot, 10 to the power 17, for example, or 10 to the power 18, then actually we never want more than one aquarium. Yeah, if 10 to the power 18, then we would never want more than one aquarium. Okay. So let's say LL lambda low equals 0, lambda high equals 1 in 18, while lambda low, lambda high minus lambda low is at least 2. We say LL lambda equals lambda low plus lambda high over 2. Then we need to let's make a function which says like PLL find ans with finds ans 1D 1D, for example. So what does it ask for? The const var r, const int k, and const ll lambda. And it returns two things. It returns the ans and it returns the key. So if a dot y is at most what? Is it most k? Okay, so ans is 118. Okay, I don't want to do it. If a dot y is at most k, then it's fine. And we say lambda low is lambda. Else lambda high is lambda. And then we continue. In the end, we have some lambda low. We again find ans 1D 1D of this lambda low, but this time we take dot x. So actually After that, we just need to subtract k times lambda low, and we get the answer. And we need to return it. So now we only need to find answer 1D, 1D given the lambda. So we have this optimization problem. It's harsh because 1D, 1D is actually not very easy. Okay, let's remember how it is done. Let's remember how it is done. So let's make a new array. TMP ij. It says, what if we only consider indices which are at most j? Then and k. Yeah, and also k ij. So TMP ij is given this I. What is the optimal answer? And this says that given this I, what is the cutting point, which is at most j actually. So actually here, what is the cutting point, optimal cutting point, which is below j? Okay. After that, we calculate all vectors k. Initially, when j equals 0, then it is always just 0. We cannot cut greater than in 0. Then, when we go from j to j plus 1, something happens. What happens? Actually, this happens. So this vector only changes its suffix to j. So if it was j and this is j plus 1, then some suffix changes to j plus 1. That's all that it takes. Okay, let's try and do it. So, oh my god. So, okay, let's start with the same thing. Let's start with the same thing, the same preparation, which is all this stuff. And actually, let's write a function cost, because I am lazy to then write it in the code. So cost ji is lambda plus ll si minus sj times j minus I minus 1. This is the cost function. Okay. Okay, let's think. So assume that we know kj. So we know if we only jump in the segments of the beginning, then what is what the what dp? No, what not what dp? Yeah. Okay, we know vector k. For assuming that we just know vector k. Vector k, we know it. We have some current vector k with some j. Then we state that when we go to j plus 1, yeah, when we go here to j plus 1, actually, the only thing that changed is that some suffix became j plus 1s. Some suffix became j plus 1s. Which suffix? We need to understand it. So we need to understand, is it true that k I j is j? How to understand? For example, let's say that j plus 1 is j plus 1, and it should be easier. It simply means that TMP ij is strictly less than dp j plus cost ji. Yeah? dp j plus 1, I think, plus cost j plus 1 I. Okay? So this, to check this, we need two things. We need cost, which is easy. We need dp. And we need tmp. So tmp is easily known because we know the current value of the current value of what? We know the current value of k. Ki, we know the current value of ki. So we can calculate this thing. Okay, cost is easy. What about dpj plus 1? To calculate dpj plus 1, it is simply tmp j minus 1, yeah? tmp j plus 1j, yeah, which we already know as well. So how can we need to a data structure k, so we need to fast understand the value of some element, some entry, and we need to assign on a suffix. Let's see how they propose this, because I didn't understand. Ah, I do it only one binary search inside already a given segment. Okay. 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 Okay, good. 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 Okay. Let's take a deck of what? So I need to store some segments. Each segment essentially is there is its beginning, its end, and the value. But in principle, the beginning is enough. Okay, let's store beginning and the value. So it's PII D. Okay, what do we do then? So we need to store the state for j equals 0. For j equals 0, all zeros. All numbers are zeros. Also, I want to store dp. Let me think. Okay, first of all, we'll dp Titan plus 1, infinity. Are you sure about that? Whatever. dp0 is 0. No, actually... Okay, dp0 is 0, it's okay. Then... In the end, I return dp dot back. I need to return dp dot back. And where... and which k gave this dp? How can I calculate this k? Okay, we'll think about it a bit later. For now, let's write this solution without finding the k, restoring the k. So I need to store this in deck. How do I store it in deck? I need to store from the point from which I have this value and which value. So it's easy. d.emplace back that from point 0 I store what? I store 0 as the best cutting point. Let's go for all j's from 0 so j always should be a possible cutting point. So it should be less than n. Okay, part 1. Note that so TMP j plus 1j is simply dp k j plus 1j plus cost k j plus 1 j and j plus 1. So this is true. Note that since the cutting point of j plus 1 is at most j, this means that we already know it. And since we already know it, we can calculate it. So this is simply dp j plus 1. Or we can say that dp j plus 1 equals what? So let's write some function, some lambda function. AutoCut equals int j int I. What do we return? Return dp j plus cost ji. Not very interesting. So we just need to cut in the point kj plus ij. It is starting in 1. Yeah, it is starting in 1. So now actually the front element of the deck is where we need to start. So we need to cut in point d.front.y. We need to cut in point j plus 1. Okay, we have calculated that. What then? Then we need to cut one element from the top, from the front of the deck. So we need to say d.front.x plus plus. However, if d.size is at least 2 and d1.x is now equal to d0.x, then we need to pop front Okay, we have fixed the vector d. Now we need to fix everything else. How to fix everything else? So we need to run a binary search and find the minimum point for which this holds. We need to find the minimum point for which this holds. Okay, let's make the binary search. So for point L, it doesn't hold. What is the point L for which it doesn't hold? It definitely... So the question is, for which point j plus 1 changed something? So I'm sure that for j plus 1, nothing was changed. Nothing, definitely nothing was changed. Okay, for which point something definitely changed? Okay, the maximum point for which we could possibly change something is n. So n plus 1 is definitely changed. So we need to find with binary search this border. So while r minus l is at least 2, int m is l plus r over 2. We need to test whether for point m the optimal answer changed. What is the optimal answer? So first of all, we need to find TMP ij. TMP ij is cut in point m with kij. Binary search is too early. First of all, I need to make popbacks. Oh my god. How it is done. So what I know is I have a function which looks like this. It's constant, then it's constant, then it's constant, then it's constant. So I need to check, is this constant preserved in the function? To do it, I need to test just this point. How to test this point? I need to take... So while d dot not d dot empty, I need to take d dot back. I need to take its point, which is x. I need to take, in this point, I need to make the substitution, which is cut d dot back dot y, d dot back dot x. So I need to check, is it true that it is actually smaller than the nuance, which is dpj plus 1 plus, well, cut, let's say, let's put it that way, cut j plus 1 d back x. So if it's really smaller, then I need pop back. Otherwise, I also want to keep track of my right border of my binary search. Again, I need to know a number which definitely changed to j plus 1. So initially it's n plus 1. But here I also know that r dot d dot back dot x also changed to j plus 1. Otherwise, it doesn't change to it. Initially L, what was L, sorry? I for some reason I removed it. Int L is j plus 1. J plus 1 definitely did not change to j plus 1. So otherwise, we know that L is dback.x and break. And here, okay, here we go. Now we need to find so while r minus L is at least 2, we say int m is L plus R over 2. We compare these two things. If cut... we know the last... So, if r minus L is at least 2, this means that the stack is not empty, the deck. And this means that we have d back y. Yeah, and we can substitute it. So, is it true that in point M, this is less than this? If this is indeed true, then in this point we change to j plus 1. We need to say that r equals m, else L equals m. Great. In the end, we simply say that d dot implies back, and starting from point r, we have j plus 1. Makes sense? It makes sense, but if j equals n minus 1, we need to break. Okay, I have written it. I think I have written it. No, something else happened. Let's put it easier. I can make an easier problem. Yeah, one crab, one aquarium, aggression 1, minus 2, minus... because I never return this number. Okay, we need to find out how we calculate the number of segments. We actually want the minimum number of segments. We want to calculate the minimum number of segments to get dp, to get such dp. In order to do that, we can simply store it in another dp. Yeah, so we can skip ds. ds is dynamic programming on segments. So VL ds. Also ds0 is 0. And again, say here that ds j plus 1 is 1 plus ds of d front dot y. And here we return also ds dot back. Well, it's a bit better, but still it is very strange. At least very strange. Ah, I forgot to add the lambda to the... No, I did not forget to add the lambda. What? Why is it 1 if I forgot to add the lambda? What? What happened? dp.back? Ah, dp.back? Wait. I minus j minus 1. Dude, what you doing? 9, 2? When this is what? When... You're kidding me. How is it 9? IJ, so firstly I... No, firstly J, then I. Okay? Does it make sense? Firstly J, and then I. Let's see. Uh... d.empty, cut... Okay, why is it saying that starts with 9? Something starts with 9. Ah, starts with 9 because... Okay, let's not push it if... So if R... is at most n, only then we push it. Zero, 92, 119. No, but better. No, but really better. Okay, I think we need to find a smaller chest. And luckily we have a stress which can do it. So let's make 1 and 1. I don't know. Okay, this definitely works. What about 19? Three, 2, wrong 4, right 1, right 2. Yes, right is 2, but wrong is 4. Okay, why is it 4? I don't understand. So I want on this test to get 2. Let's see what it says. It says that lambda low is 2. Actually, we can do it easier. So let's calculate all dp's of this function. We have 1, 1, 1. So k equals 1, only one aquarium. Then each thing, oh, okay, 6. So k equals 2 is 2, and k equals 3 is 0. The question is, for which lambda this is this k is minimal. And actually for lambda equals 2, because for lambda equals 2 we have here 8, we have here 6, and we have here 6. Yeah. So we expect to get 6 here, and then subtract 4 and get correct answer 2. However, it seems like it will not give us the correct answer 6. We have dp and ds. dp is the correct answer. So it says here that for 1 it is 2. Is it correct? Because I need to have one segment, but I have +2 fine for any segment. Yes, it definitely is correct. Okay, then we have d, increased d front. Then we make a binary search from L to R. While not the empty, so we check Okay, we know that somewhere from 2 to 4, the answer changes. Let's draw it somehow. Ah, I see. Now the answer initially, initially the answer was for 0 points, 1 point, 2 points, 3 points. For this it's 0, for 1 point it was 2, for 2 points it was 2 plus 2, which is 4, and for 3 points it was 8. But now we say that we allow to break something here. Let's see. So for segment of length 2, it's not profitable because the segment of length 2 is too small. It will get plus 2, and it's still 4. It will not be better. So it's still 0 to 4. But for 8, it's better because we get plus 2 here, and plus 2 here. So it is 6. Okay, so I expect that r equals 3. No? No? Ah, I need to do it other way. So it's better. It's worse than j plus 1. That is the correct direction. What? Doesn't make sense. Lambda low is gigantic and k is 2. But why is lambda low gigantic? It wasn't that big. So we want to find the minimum possible answer. Minimum possible answer is, of course, 1. Okay, when the segment is really big, then we need a small number of segments. And if segment is really small, then we need big number of segments. So if number of segments is less than k, then we need to say lambda high is lambda. And here we need to say lambda low is lambda. And actually here we need to put lambda high. Because exactly lambda high, the answer might be correct. What? It didn't stop? 0, 2, 32, 37. Ah. Well, this is correct. So let's make it bigger. And let's submit it and get accepted. Wow. Well, 1D optimization is really something with something. Что-то с чем-то. I don't understand what happened right now. Okay, I think I think it was enough, and I need to have some rest. Yes. Thank you for watching.